In this video, let us get to know about the process of internal conversion. Before knowing what is internal conversion, let us look at Rutherford's prophecy. Rutherford in 1914 made a statement that any nucleus, when it performs a transition from an excited state to a lower state, it emits not only a photon of light, but it can also transmit the excess energy directly to the orbital electrons surrounding the nucleus. So, this was the prophecy made by Rutherford. Okay, how a nuclear transition happens? Generally, whenever a nuclear gets excited or when a nucleus is in the higher energy state, it immediately gets into the ground state by emitting a photon of energy, what we call it as an gamma ray. Okay, the difference of energy between the two nuclear states, that is between the higher energy state and the ground state, is emitted as gamma ray. This happens generally, but in some exclusive cases, an excited nucleus may return to its ground state by giving its excess excitation energy to the orbital electrons revolving around the nucleus. After receiving this excitation energy, these electrons dislodge themselves from the nucleus and comes out of the nucleus. So, the emitted electron from the atom has a kinetic energy which equals the difference in energy between the excitation state and the ground state minus the binding energy of the electron in the atom. So, we can say the kinetic energy of the emitted electron from the atom is equal to EI minus EF minus EB. EI is the energy of the initial nuclear state, that is the excited state. Then EF is the energy of the final nuclear state, that is the after reaching the energy of the ground state. And EB is the binding energy of the electron. Since the energy of the gamma, which is equal to the gamma ray, is internally converted into the electron or internally transmitted to the electron, this process is called internal conversion. The energy given out during the nuclear transmission is internally given to the electron. So, we call this process as an internal conversion, and the electron which gets dislodged from the atom is called as a conversion electron. So, we can say this process of internal conversion and the emission of gamma ray are the two ways of making the nuclear transition. So, there may be a confusion between the process of internal conversion and the photoelectric effect, because in both the process the electron gets dislodged from the atom. See, first let us discuss about the photoelectric effect. In photoelectric effect, the light from the one atom is given to another atom. So, the light from one atom dislodges the electron from the another atom. This is in case of the photoelectric effect, whereas in case of this internal conversion, the light from the same atom is given to the electron in the same atom. So, it happens internally within an atom. So, there is a huge difference between photoelectric effect and the internal conversion. These two processes are distinct, and the spectrum obtained from this shows the energies are discrete. The energies coming out of these uh, transition are discrete and sharp. When we draw a spectrum, you will have a discrete peaks. Whereas in whereas in a beta decay, we have a spectrum of energy or the broad band of energy. Whereas during this transition, we will get the peaks, energy peaks. And during this process, when an electron gets dislodged, a hole is created there. So immediately an electron from the next higher energy state makes a transition and occupies this place. During this process, the characteristics X-rays are emitted. Okay, so what is the transition? Both this gamma decay or internal conversion may happen. So this was the probability for this was given by Taylor and Mott. In 1932, Taylor and Mott given expression the total transition probability, which is given by lambda, for making a nuclear transition from a state A to a nuclear state B is the sum of two terms. So the total transition probability lambda is equal to lambda E plus lambda gamma. So here this lambda E is called as the partial decay constants for conversion electron emission, that is for the process of internal conversion, the chances for the process of internal conversion, and lambda gamma is for the chances for gamma emission. And now we are going to define a new coefficient called conversion coefficient, which is the ratio between the two decay constant, that is the partial decay constant of a conversion electron and the gamma emission. We call it as the conversion coefficient. This conversion coefficient will give us or will describe the rate of internal conversion happening. So this conversion coefficient is nothing but it is a measure of the ratio between the total number of conversion electrons emitted over a certain time to the number of gamma rays emitted in the same transition for the same time. So we can write the conversion coefficient, which is given by alpha is equal to Ne divided by N gamma, which is equal to the decay constants lambda E of the internal conversion and N gamma for lambda gamma for gamma emission. So this is for in general. So if we take it for the H shell, K shell, L shell, M shell, for the ejection of atomic electrons from the different atomic shell levels, K shell, L shell, M shell, we can write the total conversion coefficient as alpha is equal to Nk for the kth shell and Nl to include the lth shell and Nm for the mth shell, the whole divided by the number of gamma rays emitted during the same timing. So splitting up, we can write Nk by N gamma plus Nl by N gamma plus Nm by N gamma. So each term can be written as Nk by N gamma is written as alpha k, Nl by N gamma is written as alpha L. So we have total conversion coefficient alpha is equal to the partial conversion coefficient corresponding to K shell plus the conversion coefficient for the L shell plus conversion coefficient of M shell and so on. And we call alpha K, alpha M, alpha L as the partial conversion coefficients. So there are two equations here. These two equations are called the partial coefficient conversion coefficient for K shell electrons for multipole transitions like electric multipole transition and magnetic multipole transition. See here first one is corresponding to electric pole multipole transition. Alpha K of E is approximately equal to z cube into e square divided by 4 pi epsilon naught h cross c to the power 4 L by L plus 1 into 2m e square by h cross omega, or we can write that h cross omega as e, the whole power L plus 5 by 2. And the next equation corresponds to magnetic multipole transition. Alpha k of m is approximately equal to z cube e square 4 pi epsilon naught h cross c the whole power 4 to me c square by h cross omega into whole power L plus 3 by 2. So from this equation we could see thus the conversion coefficient depends upon the Z and the energy and the order L. So from the above two equations we can infer the conversion coefficients are proportional to Z cube. It was a typographic error here. It is a Z cube, not Z3. So the internal conversion is more dominant in heavy nuclei and gamma emissions is more favored in light nuclei. So we can expect internal conversion in higher nucleus, heavier nucleus, and gamma emission in lighter nucleus. And internal conversion, I mean the multiple transitions increases with lower energy transitions of high multiple order of order L. So more the order of L, we can expect more internal conversion. So under identical conditions, it was found alpha MR, that is the magnetic multiple transitions, are much more higher than the alpha E, that is through the electric multiple transitions. And by studying about the internal conversion coefficient, we get the information about multipolarity and the parity change of the nuclear transition. And it also doesn't provide any information about nuclear structure, though they are highly helpful in knowing about the parity changes and multipolarity studies. They do not give how the nucleus is arranged inside the nucleus.